We've saved the best for last, but we now have Bogdan Zavyalov speaking on mod Poincare Duality.
Thank you so much for the introduction, and thanks for inviting me to give a talk here. Okay, so I'm going to talk about Poincare Duality and p-adic Analytic geometry, but before that, I want to discuss some previous cases of Poincare Duality, so somehow to motivate what's going on, what's going to happen later. So first of all, let me start with the most classical example of complex analytic geometry. Okay, so in this situation, we start with some manifold X, or maybe more generally complex analytic space. And we fix some field K. So I mean, it could be rational numbers, could be finite field, could be C. It will not matter much what I'm going to say. And then for any such complex analytic space, we can associate with singular cohomology groups with coefficients in the field K. And well, whatever these groups are, they are at least K vector spaces. And when we ask if these cohomology groups, they satisfy some extra properties, what one can say about it. And so it turns out that one can say quite a lot about these groups, but for this talk, I will concentrate on two main statements about these groups. So the first one, which I will call F, for finiteness, it says that if X is compact, then all these groups are actually finite dimensional. X compact. Then all these groups are finite dimensional. And what will be more important for us is that there is also duality on these groups, or these K vector spaces. So this I will denote by PD, well, for Poincare duality. And so now we need to assume that X is compact but also smooth. Compact and smooth. Well, compact, smooth. And technically I need to assume pure dimension D. You may ignore it. Anyway, so then the conclusion is that actually there are two conclusions. So the first one is that there is what's called trace map from the cohomology group H to D X K to K. And then the second conclusion is that this trace map induces a perfect pairing between HI and H2D minus I. So more precisely, this induces perfect pairing. Well, I wanted to fit here, but right here. HI XK, then there H2D minus I XK. So this admits the cup product map to H2D. And then you compose it to the trace map. So this defines a pairing between HI and H2D minus I, and then the conclusion is that this is perfect. So in particular, HI is equal to H2D minus I. Okay, so that's a complex story. And now I want to discuss, well, the goal of this talk essentially will be discuss these two statements in different geometries. And so before, and most importantly in the analytic geometry, non-Archimedean analytic geometry, but before I go there, I want to discuss first just algebraic geometry. So that's the second example. Okay, so here the setup is slightly different. So we fix a field K, which for simplicity will be assumed to be algebraically closed, even though it's not really important, but we'll simplify some notation. And we fix a prime number L. So far, I don't make any assumptions on L. It could be equal to characteristic of K, it could be not equal to characteristic of K, doesn't matter. And let's also fix a prime number k, which is characteristic of p. Sorry, characteristic of k. And well, this p could be 0. And then the basic setup is that we start with x over k, which is an algebraic variety. And then to such variety, we can associate invariants called the Etale cohomology groups. So with coefficients now in a finite field FL. And here it's important that we don't allow only finite fields. And anyway, so whatever this object is, I don't want to define it, but it's an FL vector space. And usually what people say is that it's kind of like singular cohomology, but in algebraic geometry. But to make actually sense of this statement, you need to prove properties of this construction. And so in particular, it makes sense to ask whether these two properties hold in this purely algebraic situation. And it turns out that yes, and actually, well, yes and no, and in some situations it's even better. So let me formulate precise statements now. So first of all, there is a finiteness fault. So, x, well, now we need to change compact by proper. So x is proper, and all these groups are finite. I will usually not write Etale because all cohomology groups in this talk are Etale, except for those ones.
Popco is not needed.
No, I don't make any assumptions on L.
Ah, yes, sorry. Ah, yes. Okay, sorry.
Yes, but so even more is true is that L is different from characteristics, so I'll call it F plus. If L is not equal to P, and X is quasi-compact, quasi-separated, then these groups are always finite.
X is not algebraic variety.
Huh?
X is not algebraic variety. So maybe it's just compact.
Oh, but I didn't define what it means.
I didn't have separate color here.
Well, locally finite. Anyway.
Separated the finite type.
I think quasi-separated is enough. Okay, and so then also it turns out that Poincare duality holds as long as L is not equal to P. And the statement is literally the same. So L not equal to P, X moves proper. Pure dimension D. So then, again, the first statement is there is a trace map. I will ignore Tate with for this talk, so strictly speaking, we need to put D here, but it won't matter. And secondly, it uses a perfect variant. Let me just write hi h2d minus I. Well, it's again the composition of the cup product answering this, right? Okay, so that's a story in algebraic geometry. Now, given these two examples, I want to discuss non-Archimedean geometry and see what's true there and what's not. So before I discuss the statement, let me discuss the basic setup. Okay, so non-Archimedean geometry. Okay, so now we fix a field C, which is assumed to be algebraically closed and also non-Archimedean. And well, the main three examples of such fields are the following. So one is what is called CP. You start with QP, you take its algebraic closure and then complete. It turns out that it's already algebraically closed, and so this is an example of such thing. Or also you can do it in, so this was called mixed characteristic example, and also you can do similar procedure in equal characteristics. So you can take, for example, Fp, T, and do the same procedures, or C. So, but in these examples, I consider p-adic topology. So even though C has its own topology, we just totally ignore it in this discussion. And these are examples to keep in mind. And it turns out that all three examples, the geometry over them are quite different. As we'll see. Okay, and then the main object of study is what's called rigid-analytic right over X. Sorry, over C. Well, rigid-analytic space maybe. And well, I certainly don't have time to define it precisely, but let me just explain kind of like what it's supposed to look like. So basic building block. Is a closed unit disk. Which is usually denoted by DD. And well, on the level of points, it's very easy to describe. It's literally points in C to the power of D such that absolute value of each xi is less or equal to 1. Speed of integers to the power of D. And then, well, and then you can give it the structure of rigid space. And then, so any rigid space locally looks like some vanishing locus inside this analytic, sorry, inside this closed unit. So locally X looks like vanishing locus, sorry, of some functions inside disk. And now all these things are convergent power series. Okay, so that's essentially the motivation for, well, kind of a naive picture of how these spaces look like. So in particular, it's kind of like non-Archimedean manifolds. Okay, and so then it turned out that for such spaces, one can define Etale cohomology as well. So this is a work of Berkovich and Huber, independent. They define Etale cohomology to such spaces. Its coefficients. Sorry, and L is again some prime number. Okay, so again, I mean, we are again in a situation where we have some geometry and we have some kind of cohomology theory, and it makes sense to ask whether this kind of properties hold for this cohomology theory. And it turns out that again, similar to algebraic geometry, the situation depends on the choice of L a lot, but somehow even in a stronger way. So let me be more precise. So 3.1. So if you assume that L is invertible and OK, sorry, OC. So for example, this means that if you're in the first situation of p-adic field, then you do not allow P. So if C is equal to CP, L equals P is not allowed. So in this situation, things are essentially as good as you could imagine. So let me just say that F plus holds. and Poincare Duality is false. And so this is a work of Berkovich and Cooper. So I guess I should say dates. I think this is 93, and this is 96. Well, this proved it in slightly different level of generalities, but if you combine their work, both results are true. And so the question, and I mean, if you take L equals, so and if L equals the characteristic of C, essentially the same things happen as an algebraic geometry. So I have false, but F prime and PD fail.
So this is now like another case, 3.2 million or something.
Well, yeah, 3.1 prime. Sorry. Okay, so the only interesting, I mean, as long as these two questions are concerned, the only interesting case left is if L is equal to P and your field is p-adic. Okay, so now we assume that C is p-adic. C is mixed characteristic 0 P. So for example, C is equal to CP. You don't close much if you just assume that C is equal to CP. And L equals P.
So this 3.1 prime is also by Cooper.
Yeah, I think so. Well, it's similar to like what happens in algebraic geometry. So, okay, right. So, okay, so now bad news come, is that F prime is just false. And it's not false for some like obscure reasons that somehow you can construct some really difficult space and somehow, which looks bizarre. It's false for the most basic building block. So false even for x equals to one-dimensional post-unit disk. And so let me explain this computation to show you that it's not something stretched, it's somehow how it's supposed to be, in some sense at least. So in this example, you can consider Kummer exact sequence. And then this gives you a short exact sequence which computes homology of mu p. Sorry, t square. And well, one can show that this group is just zero. The PR group of one-dimensional closed-unit disk is zero. So this map is actually an isomorphism. But the point is that this group is huge. And even its cardinality depends on the count field. So there is somehow your basic building block turns out to be non-contractible and actually really huge. But so if you change P by L, then it's zero. If P equals L invertible and LC. Okay, so as far as I understand, for a long time, somehow it was not expected that there is kind of good theory in this case. At least that's my understanding. But then it turned out that actually you can say quite a lot in this case, even though this F plus is false. Similarly as how it's false, for example, in complex geometry. And so I think the first positive result, at least to the best of my knowledge, is due to Schulze. So let me continue here. So F false. So more precisely, X over C proper. Then HI X FP Nothing. So this is due to Schulze in 2012, and the proof uses perfect techniques crucially. Crucially. And well, and then for some time there was a question: what about Poincare duality? Okay, well, and this question will be the main subject of my talk. So let me formulate the theorem. Oh, that's not fine. Okay, let me erase this. Theorem. Well, yeah, so this theorem was originally announced by Gabor in 2015, and he even gave an IGS talk about it, but then no details were written for some time, and my thesis was essentially to try to understand his lecture and write it down. So, like, following his ideas, this was first, I guess, written in my thesis in 2021. Well, the ideas are like due to Gabor, but I mean, some technical details seem to be slightly different, but essentially all ideas are here due to him. And then a different proof was found by Lucas Mann in, I mean, essentially the same time. So anyway, so okay, so what's the statement? So let X over C be a smooth and proper. Okay, so now always I assume that C is mixed characteristic. Zero P, well, and I take P. So X smooth and proper. Which space your dimension B. Then, I mean, essentially the same statement. So first there is a trace map. And secondly, it induces perfect pairing. So the first map is always the cut product. And the second map is the trace map. Okay, so that's a statement. And before I discuss some ideas that go into proof, I want to make a bunch of remarks about this statement and maybe its history. Okay, so the first remark is that, like, why is it harder than all previous cases? So the essential difficulty in proving this is that you don't have a local statement. So in all previous examples, well, maybe except for a complex, well, even in the complex geometry, you can formulate a different version if you use compactly supported cohomology, and then you can localize the question on X. But then here we see that cohomology of the one-dimensional disk, they are infinite, so there is no hope to have perfect pairing. So you cannot formulate a local statement, well, at least which is correct. So there is, and you cannot argue locally on X. So it's just false, even for X equals 1. so hard to localize index. Okay, but that being said, it turns out that the trace map was defined by Berkovich. So a long time ago, and actually it exists in full generality. Even though we don't have Poincare duality in full generality, we always have trace map in full generality, which is somewhat mysterious. So the trace map always exists for any, well, strictly speaking, I should say separated out, but I don't want to explain what it is. Smooth morphism. Of pure dimension. A more precise statement is that like trace in this case has a form R2D of lower Schrick. And so this thing is that if you assume that F is partially proper, this is due to Berkovich. This is Berkovich in 1903. He kind of didn't prove anything about, like in this p-adic situation in his paper, but he did construct the trace map.
Sorry, what does partially proper mean?
I can explain after. It's essentially it means that the evaluative criterion of properness satisfies, but it's not necessarily quasi-compact. Well, so the second claim is that in a joint work in progress with Suzanne Klee and Emmanuel Reinecke, we can define it for any F. Well, this is assumptions. General case. Okay, so the third remark I want to make is, so the QP version was known before. If at least if X is defined over fraction field of the DVR,
Sorry, does this topic cohomology sort of not change if you remove, if you pass to dense opens, sort of? Like in usual algebraic geometry, I think you can just pass to dense opens and then eventually reduce to proper.
well, I mean, here is somehow compactifications are harder.
Yeah, sure.
But does it still not change when you pass to dense open?
Well, this if you pass to the risky open, it certainly does not change. I'm not sure about general open. If X defined over a fraction field of a DVR,
Well, pass to general open, it's certainly false because D1 is open inside P1.
but it's, oh, right, sorry, yes. Even for D1 inside P1, it's false. H2 is quite huge in this case.
H2 compactly supported or
H2 compactly supported
of D1?
of D1.
Okay.
Yeah, thank you. Sorry. So if X is defined over a fraction field of a DVR, the QP version of the statement is due to Lan Liu Zhu. Hope I didn't mess it up. Yes, so the proof is somewhat different, and I mean this result by passing. Well, so hard to see that this result implies this one, but this has like much easier, well, arguably easier proof, and was known before. And so, okay, I need two more remarks. So for well, so in the open case, this QP version was also announced by Almes, Gilles, and Niziol. And well, I don't want to formulate the exact statement, but at least like if you work with pro-Etale QP cohomologies, there is also a version even for open varieties. So. But one really needs to change the statement. And the last one, so it's kind of like an expected theorem. Meaning that, well, I think we figured it out, but it's not written in full detail. So let me say, well, I pretty much hope that it's true, but not to make an ambitious statement. So joint work. Sorry. So the expected theorem is that this holds. Sorry, that Poincare duality holds for all proper maps. And the risky constructible. So that's the same joint working problems.
So you really mean no smoothness?
Yeah, so but you need to change the statement. Sorry, let me finish this and then I'll explain. So like if F is smooth and proper, then this is probably what you would imagine. But for a general proper map, so the statement should be slightly modified. So Bargov, Bard, and David Hansen, they define the dualizing complex on any rigid space over a field of characteristic 0, and then the statement should be that like as long as you restrict to the category of the risky constructible sheaves, then derived push forward commutes with duality with respect to this dualizing complex. And in particular, like in the smooth case, it recovers the usual Poincare duality. And well, this in particular implies that if U inside X is a risky open, and this is proper, and this is smooth, then HI UFP is the open H with U inside, compactly supported UFP. Sorry?
Are the groups finite or?
Yeah, they also all groups are finite in this situation. Huh?
The dualizing complex is a per shrink of the constant.
No, so in this case, it is kind of defined naively is that for a regular thing, you define it to be just constant sheaf, appropriately shifted and twisted, and then you use I upper shrink for closed emergence, and then it shows closed. But if you define this upper shrink, it will give you some wrong answer. Unfortunately.
So is there a result like this in the usual algebraic geometry or classical analytic settings then?
Yeah, so in algebraic geometry, you can just show that it always commutes with, well, I guess if you restrict it to constructible sheaves, it always commutes with duality. It follows from the usual Poincare duality. It essentially follows from the usual Poincare duality. Well, the fancy version of the usual Poincare duality. Okay, so now I want to say something about the proof of this theorem. And so I want to start with some kind of more vague ideas of what goes into the proof, and then if time permits, I will say some more precise things about the proof. Okay, I want to erase something.
Can I ask a question? So did you
Yes.
say that your theorem can imply 3?
Yes.
Uh-huh.
Well, I mean, strictly speaking, you need to show it for Z mod Pn.
Uh-huh.
But that like using Berkovich trace, Z mod Pn. Since you have a trace map for each Z mod Pn, to check perfect duality, it suffices to work at mod P.
Okay.
So this version implies it for Z mod Pn for Hn, then it implies it for Zp and then for Qp.
Okay.
Okay, so I think it's section 4. Okay, so main ideas. So essentially there are two main ingredients. Oh, okay, maybe not ingredients, but two main ideas. So the first one is to use formal models and nearby cycles. Okay, so what does it mean? It means that if I have any x, well, with mild assumptions, I think quasi-compact quasi-separated is enough. Then any such rigid space admits a formal model. That's what we'll see. So by formal model I mean that the generic fiber of x in terms of rigid spaces is equal to x. Okay, so then furthermore, it comes with a map of topoi, of Etale topoi from x Etale to y, x Etale. Sorry. Before saying this, let me also mention that there is a result of Lutke-Baumert and Temkin that this x is proper if and only if this x is proper. So in some sense, these formal models are even better than algebraic geometry. And also they are better in the sense that you have an actual map of topoi from x Etale to Kiel x Etale. This Etale. So in particular, you can always decompose cohomology of x as like nearby cycles. So just push forward along this map and then cohomology on the formal model. So R gamma x Fp is the same as R gamma x R mu lower star Fp. And now, so this is this computation of this sheaf. So essentially what we're interested in understanding, getting some control over this complex. But so this sheaf or complex of sheaves is essentially by definition local on the formal model. So in some sense it's easier because, I mean, at least if you want to prove properties of this sheaf, we can localize on the formal model and reduce it to something that we can handle. And this is algebra, and this is in some sense like the question of algebraic geometry, well, broadly understood. But this has one problem, is that this sheaf is still difficult to understand. And so here comes the second idea. I use O plus mod P cohomology. So it turns out that any rigid space, it comes with an additional structure sheaf. Which is usually denoted by O plus. And well, its definition is really easy. So it just sends an open U, or Etale open U to functions on U such that its value at each point is less or equals than 1. So this is a sheaf of ZP modules, but not QP modules. Not QP modules. So in particular, it makes sense to take it mod P to get something non-zero, and we will exploit it. Okay, so now I will erase everything here. Okay, so there is a short exact sequence, so inversion of Artin Schreier. Fp sits inside O plus mod P, and there is a surjective map to O plus mod P, which sends a function f to Fp minus Fp. And then the primitive comparison theorem it says that cohomology of Fp are actually not that far away from cohomology of O plus mod P. In the sense that if you tensor it with OC mod P, your ground field or ground free, well, clean of integers, this has a natural map to Hi of X O plus mod P. And this map is an almost isomorphism. Almost isomorphism. I'll explain in a second what it means. So this means that kernel and co-kernel are killed by e to the power of 1 over n for O n. It's not quite an isomorphism, but current, like the difference is like killed by very small portion. Anyway, so using this, yeah, so this is Euler Schwarzer. So using this, you can like there are standard methods how to reduce questions about Fp-cohomology to questions about O plus mod P cohomology. So using standard machinery, well, now standard, one can reduce Fp duality to almost duality or R gamma X O plus. Okay, so the things that we win here is that now now we combine it again with idea 1. So we choose again formal model, and we have R gamma X O plus mod P is the same as R gamma X R mu lower star of O plus mod P. Okay, so we get the same, and let me now put P equals 0 here. I mean, we can just technical. So this is local again on X, but now it has an advantage that it's actually computable now. So this is due to almost purity of Schwarzer, of Hawkins Schwarzer. But this is, but again, this part is essentially algebraic geometry. I mean, it's like non-Euclidean algebraic geometry, but I mean, well, I mean, nowadays we're not afraid of this. So this is algebraic geometry. Okay, so that's roughly the plan. That like you want to decompose studying this object into separately studying this question, which is like now local but difficult, and then global study of like an algebraic geometry. But since it's algebraic geometry, this part was actually easier. So the hard part is now local. The hard part is understand. Okay, so now I want to say yes. Okay, I have 14 minutes, so I can say how you actually study these things in slightly more detail. So sketch of the problem. Okay, so let me repeat again what we want. So we want duality of the form, or almost duality. So this. And it's some kind of trace map which we still need to define. Okay, so for this there are essentially 3 steps. So the first step is okay, and so also let me mention here is that we remember that OX is decomposes this way. And also remember that a theorem of Lutkin, Bombard, and Temkin tells us that this is actually proper. So essentially 3 steps. The first step is to show that this gadget is like very close to be coherent. And then the second question is to prove duality for this thing. Prove local duality for star plus T. And this is in some sense analogous to the theorem of Gabor, that analytic nearby cycles commute with duality. Analogous. Gabor's theorem. Nearby cycles. Commute with duality. And then the last step is use Grothendieck duality on X if P equals 0. Somehow, like you want to combine this duality for the nearby cycles and duality on the generic, on the mod P fiber. And so, like we are in the realm of Grothendieck duality by step 1. I mean, I haven't yet formulated what it means exactly, but it's like really close to coherent duality. So the coherent shift, so you can use some version of Grothendieck duality. So use Grothendieck duality. So I don't want to talk much about 3. It's kind of delicate because this thing is not Noetherian. And it's kind of delicate because sheaves are not coherent, but only what's going to be almost coherent. But in some sense, it's quite straightforward. If you are if you kind of keep track of all these subtleties, it's not that hard. So it's not subtle, but not too difficult. So I will concentrate only on steps 1 and 2. Okay, so now I want to discuss first step 1, at least a little bit. Okay, for one, since I don't have much time, let me just formulate the result. Well, it turns out that if X over all C is an admissible formal model, admissible formal scheme of dimension D, and it's complex. Well, so it lives in degrees from 0 to D in the almost sense. So this is in the almost sense. And it's almost coherent. So what it roughly means is that each Ri can be approximated by a coherent sheaf up to any small portion. And also, somewhat surprisingly, it turns out that it's also quasi-coherent on the nodes. Okay, so essentially that's the result. I don't want to go into the proof. Let me just say that the proof is similar, somewhat similar, well, very much motivated by Schultz's proof of finiteness of Fp-cohomology. So somewhat similar to Schultz's paper on p-adic. And also, this statement implies this finiteness of Fp-cohomology. This finiteness, so like finiteness is encoded here, so turns out that this is kind of the crucial part of the proof of finiteness. So, okay, so that's for it. And now let me say a couple of words about 2, which is probably the most interesting part. Again, so here, as always, there are 2 steps. First, define trace map, and then shows that it commutes with, like that it induces almost perfect pairing. So 2-1, define trace. So here, trace should be a map from R mu over star or plus mod P, sorry, shifted by 2D into coherent localizing complex. Right, so we already know that this is very close to be coherent, and to make sense of this, I think it's good to think about this in a slightly different way, which is clearly the same. So about this sheaf, one should think about as you take dualizing Etale sheaf, and then you tensor it with all plus mod. So then it looks more in the spirit of the fact that nearby cycles commute with the bound. Okay, so we need to define this map, and essentially, well, the key ingredients is on the smooth locus, it's essentially defined in BMS1. Then on generic fiber, it's essentially defined by Schulze. And then in general, you glue them and extend from 4-dimension 2. Yeah. I mean, this could be made precise if you are, like in this case of a scheme, not a formal scheme, and also over DVR. Then you can use some reflexivity of some sheaves to do it precisely. In this situation, somehow this 4-dimension 2 doesn't quite make sense. So because generic fiber is not really in the formal model, but somehow motivated by what's going on in schemes, you can make somewhat similar arguments, but which are much more ad hoc, but to work. Anyway, so essentially, the hard part is to show that they coincide on the intersection, and then well, the hard part really is to make this extension argument. Okay, so that being said, it gives you some map, and then once you have a map, then it's a property that it induces perfect pairing. And so this can be checked kind of locally. So let me formulate a meta theorem. Yeah, that takes care of 2. Sorry, so 2.2 check that well, this trace induces an almost perfect pairing. And then I want to formulate it as a meta theorem, though, like it's a precise mathematical theorem, which is some kind of local uniformization or some kind of alterations in this world. So the actual statement is to temp. Well, I guess I should say first Hartle in the case of EDVR, then Temkin. And then, I mean, Temkin's version is not quite enough with this meta theorem to hold, but so we need to slightly modify it. So it's one was done by me, but essentially it's due to Temkin. And so the meta theorem says that if one wants to prove a statement EX for all Dixon admissible formal C schemes, then it suffices. Like to prove it in some cases. Suffices to check. One, Px is a risky local. Px sense through weak isomorphisms. Px descends through nice finite group quotients, and Px falls to polar stabilize. And so in our situation, so this is an explicit computation. This is just obvious. This is Grothendieck duality. Well, this is growth inequality plus some actual arguments.
What does nice mean?
Yes. So nice means that you have a formal mod of X, a generic fiber is smooth, you have an action of G, and you assume that, so Gx on generic fiber, and you assume that this action is free. So then you have quotient is also smooth. And you can check that this is a quotient of, so this is generic fiber. So you need to check if you know the statement here, you can descend it to X mod G. You don't assume that here action is free. Anyway, so this is an explicit computation. This is, I mean, essentially by definition, this is literally growth inequality if you unravel this, and this is the hardest part. And well, I don't have time to explain it, but one of these ingredients is also growth inequality. And I want to stop here.
Are there any questions?
Explain how polystable Gauss-Maybe from the Young or Temkin local uniformization.
So it's essentially Temkin's local uniformization, but the problem is that in Temkin's paper, he argues Etale locally on the generic fiber, but then it's not true that Etale locally, like if you have Etale morphism on generic fiber, it does not necessarily lead to an Etale morphism on formal model. And we cannot localize the problem on X, we can only localize the problem on formal model. So you need essentially to check that all his proofs give you more than he states. But that's what I'm saying, essentially it's Temkin's result.
So these fine groups come that because you need alterations, some enhanced version rather than just having resolutions.
Yes, well, yeah, it's kind of similar to, I think, the Young's paper where he does resolution up to finite.
So what is the statement P of X in your context exactly?
Oh, sorry, in my statement, P of X is that, where is it?
Perfectness of the theory.
Sorry, I didn't formulate, sorry, yes. In my statement, P of X is that the map that this pairing is almost perfect. And so it's hard to check on an arbitrary formal model by itself, but using these reductions, you can be reduced to this conclusion.
Would you remind me of the ideal construction trace map?
Right, so that's what I,
Yeah.
so that's what I was trying to say here. So in the,
There, I forgot.
yeah, so I mean, I'm saying that, so you mean that like what goes into here and here, or?
Yeah.
So
Basic idea, yeah. Is it inductive? You reduce to projective space or projective line or what? No.
oh no, so here essentially what you need to compute is you need to compute, as far as I remember, you need to compute push forward, well, sorry, mu from Etale, sorry. X Etale, mu to X Etale, and you need to compute that this is a mega plan up to some, I don't remember, I think -1, but up to some twist. And well, once you know this, then essentially you pass through wedge powers.
You use the trace map for differential.
Sorry?
No, I don't know. Once you have that, how do you define the trace map?
Oh, so this is essentially a generic fiber. So, I mean, if you don't use mod P and you use this, then you take a generic fiber of this, then it will be essentially this in degree 1.
Mm-hmm.
And then you just pass to wedge D. And you can show that if you also don't put P mod 0, P equals 0 here, then a generic fiber, like this dualizing complex, will be exactly just differential, well, of differential forms. And in BMS, I think they do something similar, but it essentially comes from functionality of the cotangent complex and some computation with cotangent complex, as far as I remember.
Which cotangent complex?
I think, sorry, I think it's like OX pro Etale, sorry, O plus pro Etale over ZP. But well, I didn't look at this paper for some time, so I might misremember. Sorry, did I answer your question?
Yeah, yeah.
Okay, sorry.
Could discuss more.
Okay.
Any other questions? Thank Bogdan again.